the equations of motion and the laws of motion we discussed so far describe only the motion of point particles. Now, these balls can be approximated as point particles. The motion of these are simple parts, and so the equations and the laws of motion can be applied to these particles. But when it comes to objects like this, extended objects, if you allow these extended objects to move, it will not be as simple as the motion of these pointed objects. Or if you want to allow this meter rule to move, if you look at the way the meter rule moves, or this object moves, it's a complicated motion. Look at that. Different parts of the object have different motion. Is that right? And therefore, in order to apply the laws of motion or the equations of motion for objects like this, which we call extended objects, we define a term called the center of mass. In other words, when you want to describe the motion of this object, rather than looking at the complicated motion of the whole object, we can look at the motion of one point on this object where the whole mass of this object may be assumed to be concentrated. Now that point is called the center of mass of the object. Now I have a fair idea where the center of mass of this object will be. Tell me, is the center of mass at the center of this rod? You can see there is a ball at the end of this rod. Means the mass of this whole thing may be assumed to be concentrated at a point close to that ball. Now, how do I detect the center of mass? If I have a meter rule, I can detect the center of mass by actually trying to find the balance point. Look at that. The meter rule is actually balancing at this point, which means the whole mass of this meter rule may be considered to be concentrated at this point. And this point, therefore, is called the center of mass of this meter rule. Well, the weight of the object will be acting vertically through that point. You see that? And I am supporting that weight. That means this object stays at equilibrium. If I try to balance it at any other point, what happens? The meter rule falls off with a complicated motion. Now look at the way this object, I'm going to try and balance this at its center of mass. Let me see if I can find the center of mass. There I have found the center of mass. Now if I drop it from the center of mass, its motion will be simple. It simply drops like a point object. You see, it simply drops like a point object. Whereas if I want to drop it, say if I am going to support it here and I drop it, look at the way it moves. It has a complicated motion. And if I want to move it from a point on the other side, again it has a complicated motion. So the center of mass, when you want to consider the motion of an extended object, it is the motion of the center of mass that we consider. Therefore, to locate the center of mass is an important skill, and we will be talking about how to locate the center of mass of a system of objects if the system of objects are distributed at different locations in space. Now, if I have two cars, for example, now if I place two cars on this track, I have two cars here, and you can see the two cars moving. The motion of the two cars can be studied by locating the center of mass of the two objects and then studying the center of mass of the motion of the center of mass. We will talk about all these things in this class. Alright, these animations show the motion of the center of mass when an object is projected at different points. If you notice the first diagram, the object is projected vertically at its center of mass, and you notice it is moving as though it is a point object. Now on the diagram here, it is projected at a point on the right of the center of mass, and you can see the object tumbles as it climbs. But the motion of the center of mass has not changed. The motion of the center of mass on the left diagram and the motion of the center of mass in the second diagram are exactly the same, although the motion looks complicated in the second case. Similarly, the third case, the object is projected from a point to the right of the center of mass. Again, it tumbles the other way, but again, the motion of the center of mass remains exactly the same. The motion of the center of mass can be approximated as the motion of a point particle. Let me also show you when these are projected. We got three diagrams here. The top diagram shows a gun projecting this object at the center of mass. And you can see its motion is very simple, just like you project a ball. And in the second diagram, the projection is done above the center of mass, and you can see how it tumbles. But look at the path taken by the center of mass. The center of mass falls as though it is a point particle. In the diagram below, the projection is done below the center of mass. Again, the object keeps tumbling, but the center of mass follows the path followed by the first case. In other words, the path taken by the center of mass is as though the center of mass is a point particle. Okay, let's now look at how to locate the center of mass of various systems of objects. We will now look at the positions of two cars and how to determine the center of mass of the two cars. Well, a car of mass m1 is at position x1. Well, let's bring the car. This is the car of mass m1 at position x1. And another car of mass m2 is at position x2. We have two objects. An object of mass m1 placed at x equal to x1 on the x-axis. An object of mass m2 placed at x equal to x2 on the x-axis. The center of mass of these cars will be somewhere in between. It will be closer to the bigger car than to the smaller car. In other words, center of mass is a point where the two masses can be assumed to be concentrated. So the center of mass of these two cars is at x center of mass, somewhere here. Now, so that the combined mass of these cars can be assumed to be placed at that point. That means the motion of these two cars can now be studied as the motion of their center of mass. The motion of two objects can be summarized by considering the motion of their center of mass. The motion of the center of mass can be approximated to be the motion of a point particle. Then we can apply the equations of motion and the laws of motion we discussed so far. The x center of mass can be measured. I want you to take note of this equation. Now, what is x center of mass? Where is the center of mass along the x-axis? X center of mass can be written as x center of mass equal to m1 x1 plus m2 x2 divided by m1 plus m2. In other words, the position of the center of mass of these two objects is determined by the masses of the two objects and the positions of the two objects. The position of the center of mass, called x center of mass, is m1 x1 plus m2 x2 divided by m1 plus m2. It's a very simple equation to remember. Now, if there are n objects on the x-axis, not necessarily two, there are many objects on the x-axis, then we can extrapolate that equation. m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 divided by m1 plus m2 plus m3 plus m4. And we can summarize it like this. X center of mass equal to summation I equal to 1 to n mi xi. I hope you understand these notations. When I equal to 1, mi xi will be m1 x1. When I equal to 2, it will be m2 x2, and so on. We can do it for n number of objects. In other words, summation I equal to 1 to n mi xi means m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 plus all the way to mn xn to the nth particle, and divide that by what does this uppercase m stands for? Is m1 plus m2 plus m3 plus m4 all the way to mn. So if there are n objects on the x-axis, the position of their center of mass will be given by this equation. X center of mass equal to summation I equal to 1 to n mi xi over the sum of the masses. Now, similarly, if you have this n objects on the y-axis, then their center of mass will be somewhere along the y-axis, and we can represent that by y center of mass. Can you write a similar equation for that? It will be y center of mass equal to summation I equal to 1 to n mi yi over summation I equal to 1 to n mi. Well, this is what we call m1 plus m2 plus m3 plus m4, or which is the same as the uppercase M. So, if you remember these two simple equations, you can find the position of the center of mass along the x-axis and the position of the center of mass along the y-axis. Now, very often, objects will be scattered in the xy plane. That means the center of mass will then have an x position and a y position. The x position of the center of mass will be obtained using this equation. The y position of the center of mass will be obtained using the lower equation. All right, let's see